Hello, this is Dhanush. Today in this tutorial I'm going to speak about base trees in file structures. The objectives of this study are to answer some of the few simple questions. They are: what are B trees? Why are B trees used in file structures? What are the operations performed on it? What is the performance of B trees? And what are the implementation issues of B trees? B tree is a tree data structure that keeps data stored and allows other operations that are to be performed in it. It can have more than two children. That is, it is just a generalization of a binary tree. They are commonly used in databases and file systems. In B trees, the internal, that is the leaf nodes, can have a variable number of child nodes. When the data are inserted or removed from a node, its number of child nodes changes. In order to maintain the range of the B trees, internal nodes may be joined or split. B trees do not need rebalancing as frequently as other self-balancing search trees. Some of the characteristics of B trees are given here. Of this, the most important are: the height of the tree must be balanced, and a B tree is generally characterized by the number of elements present in each node. It is called as the order. The typical structure of the node of a B tree of order 4 is shown below as you see it. A B tree having order of m signifies that all nodes can have maximum m child nodes, and the root node can have nodes ranging from 0 to n, whereas the other nodes can have nodes ranging from m by 2 to m elements. Indexing helps us to search records in files effectively, so that the operations such as insertion, retrieval, modification and deletion of records could be done. We could also search for the record present in the file by one single access to the file, which is one of the ideal goal of file structures. The question that arises here is: what if the index itself increases in size due to large amount of data? How could we reduce the size of the index file that is present in the primary memory? B trees provide an appropriate solution to this problem by indexing the indices, so that the ideal goal of retrieving the data in a record by a single access can be accomplished. These are some of the common operations that are performed on B trees. Taking an index list, we could create a B tree using the following specified rules, which are used in an example that is followed. Now we consider an example to understand the creation of a B tree. The input keys are the alphabets, and we consider the order of the B tree to be 4. As the order of the B tree is 4, we insert the first 4 alphabets in the alphabetical order into a node. To insert T, we must split the node equally as the order of the node is 4 and promote the highest element from each node to a new parent node. As Y is alphabetically greater than W, we insert Y in place of W in the parent node and make W available in the child node of Y. In order to insert U, we need to employ the rule of splitting the child node of Y and insert U. We then promote the highest element of the third child T to the parent node. We just insert I and O in the child nodes of Q as they are alphabetically lower than Q. Similarly, in the same manner, we insert P, A, S and E in the child nodes of Q, I, T and I respectively, and rearrange the child nodes in the sorted order. To insert F, we need to split the child node of I and make a parent node for the split nodes, and then insert F at the lowest appropriate child node, that is, as lowest child of I. The highest element from the parent node of these two child nodes must be inserted into the root node. We must again split the root node and promote the highest element from the child node to the root node. In order to employ this, we insert J as the child of Q. To insert K, we again use the same rule of splitting the child node and inserting K in the child node of O. We just simply insert L in the child node of O. To insert Z, we insert Z into the root node and then split all its child nodes to insert Z in the child nodes and depromote Y as the child of Z. We again split the child node of Z to insert X. Employing the above rules explained, we shall insert all the indices into the tree and get the finally required binary tree as shown here. Redistribution of keys. Consider the status of B tree given in the figure. The fourth node of the second level is full, and insertion of any element into that node causes tree to grow by one more level. There can be a small change in the methods that the keys are inserted, so that the frequent split does not occur. In this figure, it is observed that the first, second and third nodes are having elements less than their maximum capacity. Therefore, instead of splitting the fourth node, the keys in the third node could be shared with the third node. Thus, this makes the fourth node postpone its splitting to a later stage. Similarly, if the third node is full and an element has to be entered there, it can share its key with the second node. The B tree after redistribution appears as shown. Now we consider the deletion operation in a binary tree. We shall consider X as the element to be deleted. Start with the root node and reach the node containing X. If X is not a maximum element in that node and deleting X may not cause the node underflow, then just delete X. If X is not the maximum element of that node and if deleting X does not make the node underflow, then delete X and merge the node with any of the sibling node and update the parent node. If X is the maximum element of that node and deleting that node does not make an underflow, then delete X and update the parent node. If X is the maximum element of that node and deleting X makes the node underflow, then delete X and merge the node with its sibling node and make changes to the parent node. The process of merging in case of deletion follows the same procedure as explained in the redistribution of keys of B tree. During the insertion and deletion operations of B trees, it should be noted that none of the properties of B trees should be violated. Now we shall consider the performance of B trees. The worst case of searching in a B tree is when the last element of the last node is to be searched. In other words, the depth of the tree is an indicator of its worst case search. In general, a B tree of level D has a minimum of 2 into m by 2 to the power of d minus 1 leaf nodes. If a B tree has n keys, then n is greater than the number of key nodes. For a B tree of order m and n keys, 1 plus log n to n by 2 to the base m by 2 is the number of searches that are required to find an element. The time and space efficiency statistics of B trees to search, create, insert and delete are given below. We shall now discuss about the issues of the implementation of B trees. It is in general the practice to have separate structure for B tree and B tree nodes so that we can separate the maintenance of B tree and B tree nodes. When a B tree is created from an index set, different structures are necessary for the leaf nodes and the index nodes, as this will implement the B tree to its fullest possible extent. The order of the B tree is the amount of memory available for the application. It can be stored in a file or can be created each time the application is run. It is the designer's choice to decide on its depending on the cost and benefits of each situation.